All right, I can see that you're recording now.
Okay, good. Yeah, sorry. Yeah, let's start again. Yes.
Okay. So start from J. Like you have n chocolate making tabs. Each tab, the ith tab has the ability to produce from AI to BI milliliters of chocolate per second. Um, and it produces chocolate at a constant temperature, which is Ti. They give all of that to you. So suppose that they suppose that all of the n taps are adjusted to produce x1, x2 to xk milliliters of chocolate per second. And those x must satisfy the constraint of A and B that we mentioned before. Then the temperature of the resulting chocolate when we mix all of those chocolate together is like it has to satisfy. It can be calculated using this formula. So x1, t1, x2, t2, adding all of those up, divided by the total amount of chocolate. So what they ask you is, okay, they give you all of the chocolate tabs. There are k of them, which is 10. Oddly enough, it's very small. And they give you like queries. With each query, they will give you two factors. First is the desired temperature of the chocolate you want to make, and the second is the amount of chocolate that you want to make per second. So the first one is equals to this. The second one is equals to the denominator. I believe that's the right word. The denominator of this equation. And you want to find a way to assign x to each chocolate tab such that these two values are satisfied. So print out yes if it's possible and no if it's not possible. Okay, so for the problem, because k is oddly small, we can think of we can try to solve for like each query independently, and we loop over k somehow. So there's a way to think about this problem, because we are fixed on the amount of chocolate, like the amount of chocolate that we need to produce is fixed, and the temperature is also fixed. We should try to like unfix one of them, because both tools are fixed, then it might be difficult. So here I will try to unfix the temperature. So let's say I want the amount of chocolate fixed. So what information can I derive? Maybe I can derive into like the minimal temperature that I can achieve and the maximum temperature that I can achieve. Then I can check if this temperature that they give me is within that range. And you can actually reason that this approach turns out to be true because like when there's an assignment of the smallest, like the minimal temperature and the maximal temperature, then we can basically do very small steps to go from the smallest one to the largest one. And that means that every temperature within that range can be covered somehow. So yeah, so I will turn the problem into like you have a fixed amount of chocolate per second and you want to find the minimal temperature and the maximal temperature. Doing this is just really easy greedy. First, you have to start from like for every chocolate tab, you have to start from AI, and then you start from the chocolate tab that has the smallest temperature, like the lowest temperature, and then you try to fill up, and then go to the next lowest temperature, and then you try to fill up, and you keep doing that until you reach this amount. Similarly, you can do a similar like greedy for the largest, like the highest temperature by going from the highest temperature tab to the second highest temperature tab and so on. Yeah, so that's J. Yeah, that's J.
Wow, nice.
Yeah, it's actually pretty simple.
This would be a bit harder if you had to like construct the solution though, right?
Yes, constructing the solution is harder. And I actually, there was some previous attempts that it was wrong that made me think about like maybe this problem requires x to be integral or something, but it turned out that I actually had just overflow problems. So that was dummy.
Okay.
Okay, so I think K is the next problem we can discuss because the solution turned out to be pretty elegant. So for A, so the statement is like this. So you have two integers. So you can, there's like this really elementary additional method that you go through each column, each 10 digits, and then you add up. And then if there's like, if the result goes over 10, then you have one carry over to the next column or something like that. So the protagonist of this problem does not know how to remember how to carry. So instead, he do something like this. So he will subtract one. So he will repeatedly subtract one from a number and add one to the other number until he get two numbers that can be added together without having to carry at any point. So for example, for this 1099 test, you can see that if we add it normally, you have 9 here, 1 plus 9 equals 10 here, so you have to carry right here. So that's not good. But however, what you can do is to subtract 1 from 10, add 1 to 99, so it becomes 9 and 100. And you can see that this addition does not have any carry. So they want to know what is the minimal amount of operations you need to do before you can reach two numbers that can be added without using any carry. Cool, and the digits are large. I mean, the numbers are large. It has 10 to the 6 digits. Cool. So let's start. We have to solve this quickly somehow. Yeah. So one thing we can see right away. Oops. Yeah, there we go. One thing we can see right away is that at the end, like after any operation, the sum doesn't change. So maybe we can compute the sum first. So let's say 1 for 10, 99, the sum is 109. Okay, cool. The second observation is, let's say the first number is transformed into A, the second number is transformed into B. So because of the non-carry addition property, the resulting digits of A, if we lined up with the sum, so A is like this, and remember that A we have like 0, 0, it's like 9 or something. If we line up, then for every column, the digits of A must be less than or equals to the digits of the sum. That is because of the non-carry addition properties. Similar with B. But it turns out that we only need one of them to be satisfied for the other to be satisfied. So that's out of the question. Okay, so let's suppose that we can solve this problem symmetrically. Let's suppose that we turn the first number, just subtract from the first number and add to the second number. So we want to know the number A that is less than or equals to 10, such that it satisfies the property that every digit is less than the digits from from the sum. So my solution was to do a greedy of some sort like this. So I will line these two numbers up, digit by digit. So if like, for example, if the current digit of the current digit of the original number is less than the current digit of the sum, then I will assign the current digit of the original number here, and then I will just copy everything from the sum here. Or else I will use the sum to, okay, let's demonstrate this with another test. I think it's no. Let's demonstrate this with second. So if the current digit of the second number is less than or equals to the current digit of the sum, then we assign it or else if it's larger, then we will assign the current digit of the original sum, and then we will copy the entire suffix of the sum into the answer. I don't think my reasoning makes sense. I mean, I don't think my explanation makes sense. So similar, like my reasoning is that like because we want to make it smaller than the original number, but we also wanted to make it as large as possible. Then at each digits, we will try to use the largest digit such that it doesn't overflow. It doesn't becomes larger than the original number. So yeah, I came up with that really.
So yeah, so my solution is I think it's equivalent, but the reasoning is slightly different. So essentially, what I'm figuring, the first thing I'm trying to figure out is where is the highest digit where a carrying occur.
Okay.
So for that digit, then in order for the remainder addition to have no carrying, then I have to make one of the digit essentially higher, one higher. So the carry already occur by doing this add one, subtract one.
Okay.
And when I do that, I basically weight that digit one digit higher than it is, then everything else should be 0.
Okay.
So then I just need to figure out for these two numbers, which one, when I go to that state, I can use a smaller number. So I basically just compute the two string and then keep track of which one is smaller, and then output that.
Okay.
Yeah. So essentially, because that carry has to occur, then that's basically the goal, to make the highest digit carry already occur. And when that occurs, then obviously every other digit just be 0 is the optimal choice.
Okay.
Yep.
I think it's similar.
Yeah, it's equivalent. It's going to be equivalent. It's just how to view it. Yeah.
I see. Yeah. So anyway, the problem is very greedy-like, and yeah, it's pretty good in my opinion. Okay, cool. So I think the next problem we should discuss is
maybe. So yeah, I think maybe you can discuss D, but before H, I think maybe we should cover the easier problem first before we move.
Okay, sure.
Okay, I can do that.
Okay, yeah, after D, then yeah, Richard can discuss.
Okay, so for D, they give you like this dam model where each dam has a water flow to one of the parents' dam or the city. And each dam has a capacity, like how much water it can hold until it breaks, and its current water amount in that dam. So your goal is to add some more water to some to just one location only, some more water to one location only, such that the water will, okay, so if you add it, then the water will break the dam, and if it keeps breaking the dam until the city, and if the amount of water that floods the city is no smaller than this W they give you, then you're good to go. So you basically want to choose a city and the smallest amount of water you need. I mean, choose a dam and the smallest number you want to add to a dam. Yeah. So they actually give you like the model of a tree where each dam has a parent's dam, either a parent's dam or like the city itself. So for example, for this test, let's actually draw the tree out. There we go. So let's say this is the city. Then the first dam connects to the city because it has the 0 mark here. And this is the first dam, and it has 1500. The second dam connects to the first dam, and it has 10 over 49. The third dam also connects to the second, to the first dam. It has capacity 0.50, and the fourth one is connected to the third dam with 48 and 50. And you would want to flood this with the amount of 75. So the optimal strategy for this is to choose the fourth dam, add two units of water to it. So it will become 50-50. That means that the dam overflow. So that amount of 50 goes to this dam, which also overflows this dam. So that amount goes to this dam, which also overflows this dam, because 50 added to 50 is 100. So 100 units of water goes to this city, and it overflows the city because the threshold is 75. So yeah. So a property you need to notice is whenever you choose a city, the first objective you want is to add some amount of water such that it breaks every dam from this city up to break every dam from this dam up to the city. So that's the first objective you need to clear first. So using that, I have a DP where tuple of U is the minimum number of water I need to pour into U, such that it breaks every dam from U up to the city. The second thing you want to see is that this amount of tuple will combine with all of the water that is already essentially in the dam, from the path from this dam to the city. So that means that if you add this amount top U to the if you add this top U to the dam U, then the amount of water that will flood to the city will be the amount of top U plus sum of all of the water that is already on the path. And yeah, and then if this number is if this number is larger or equals to W already, then you don't have to care anymore. If this number is less than W, then you just add that constant amount to this dam U to make it enough to flood the city. So I calculate this top U with DP. Basically, I want the amount to first topple this city. To topple this dam, and I want this amount to also be enough to topple from this path to this path. So I calculate top U based on top parent of U, and yeah, just iterate that over all of the vertices, and we can get the solution. Yeah.
So your top U is the minimum amount you add to U that will overflow all the way to
the city.
To the city.
Yes.
Okay. And you compute this from root down, so you can push some information down to this.
Yes.
Okay.
Mm-hmm.
So I solve it using bisection. By basically checking each amount and then compute how much water you get for each node. You basically take the max of your children, because you can flood only one of your children branches.
I see. Okay. So yeah, that's T. I can leave the host to someone else.
Yeah, let Richard go, and then Riley, and then we'll, I think, come back to you.
Give me a second. I lost the meeting controls. I can't find how to unmute permanently, but it should be fine. Okay. Well. Okay. So out of these problems, I think the easiest was M. I don't know if it's worth even talking.
Let's not talk about M.
Yeah, M is too easy. So C, coin stacks. So A and B are playing a game. Basically, every single turn, A and B have to remove a coin from a stack of coins, except they can't be the same stack. And so all you have to do is to check if it's possible to remove every single coin. And well, this this can be constructed because it's just you only have like 1,000 coins. Riley showed me this last week, I think. But basically, just continually take each stack, the two largest stacks, and then take one coin off the top of them, and then put them back in, and then just keep doing that over and over again. And then if you have a solution, then it'll construct it. So yeah, it's not that bad. Problem A.
So yeah, I would like to say C is like NAQ problem E reduced to this essentially.
Yeah. Okay. So problem A. So you're given a sorted list of numbers, and what you want to do is to change one digit such that the list of numbers is no longer sorted. So like here you have like 142 4711 9876. If you change this number right here to 3876, which is just one digit change, then you can like make the list no longer sorted. So this problem is also not that bad. So first thing you notice is that if the two numbers have like two different amounts of digits, so like one has one digit, 42 has two digits, you can't really change any number to make one bigger or less than the other. So you basically ignore any pairs of numbers that have like different amounts of digits, and you only focus on numbers with the same number of digits. Also that like because you only have to like switch one pair to make it no longer sorted, so you also only focus on pairs of numbers rather than the entire sequence. And all you have to realize is that you only ever have to change the leading digit of the number, because if one of them if they have like this, you can either change this leading digit to 1 or this leading digit to 9. And so essentially, if neither of those work, then obviously that doesn't work. But if basically that's like the most change that you can make, and if that change doesn't work, then the pair of numbers can't be touched, basically. So yeah, that was pretty simple logic.
So yeah, I saw you have a few submissions. So what were the problems?
Integer overflow.
Integer overflow.
Because things can go up to 10 to the 5th, and I accidentally used an int in one of the calculations, so it messed up. Okay. And then G was kind of fun. So essentially, you have a list of numbers made out of 1s, 2s, and 3s. So you want to create like a quote-unquote set list out of those numbers where you select numbers from this list in order. And so the first number of the list must be a 1. The last number of the list must be a 3. And then all numbers in the middle have to be 2s. So let's see here. So for example, in here, we can select any of these 1s to be the first number, any of these 3s to be the last number, and then the 2s in the middle, they can be selected like however many 2s that you want, as long as there's at least 1 2. So the observation here is that like this is basically just calculating the choose function, the sum of the choose function, which is known to be 2 to the n. So for example, here, if we can choose any of these 3 2s, as long as there's 1 2, so that's 2 to the 3 minus 1. Okay, and essentially, it becomes slightly more complicated for like ones that happen like this. So for example, here, if you choose this one, then you can choose this too. But if you choose this one, then you can't choose. If you have this one, then this 2 is like off limits because this 2 comes before the 1. So but the thing is, you don't really have to worry about like the exact order. You could just like do this in just math, I guess, because for every one that appears, so we can have like a running sum of possible combinations. So let's just call that S. Whenever a 1 appears, you just add 1 to S. Whenever a 2 appears, so if 1 appears, add 1 to S. If a 2 appears, add multiply S by 2. And if a 3 appears, then what did I do again? If a 3 appears, then you just add S S minus the number of 1s that appeared earlier to the answer. So this works because for every single time that a 2 appears, you can think of like the number of 2s here increasing, I guess. So like, for example, if you add a 2 to these 2 2s already here, then what happens is that, what is it called? You add a number to these 2 2s. So here we have maybe, if we wanted to select 2 to the 2 minus 1, and then if we added a 2 to like this running sum of 2s, then we would have 2 to the 3 minus 1. And so we can just ignore the minus 1 for now, since we can just like include that in like the calculation of the answer later. So you notice that it's just 2 to the 2 and 2 to the 3. So you just multiply it by 2. And then if there's a 1 that appears, we know that we have another choice of like a 1. So we can just add 1, and then every single time a new 2 appears, then that 2 is associated with that 1. So then that one, this new 1 accounts for it. I don't know if this is making sense or not.
It's slightly suspicious. So I guess this multiplied by 2 part. It's so what you're for 1 and for 2 you're maintaining the same thing. It's the same S.
Yes.
Okay, and then why would this one, if you just have 1 and then the second one 2, why the multiply by 2? Because if you have, let's say you start with 1 and then followed by 2, and then followed by 3. Oh, you have a what? You have a subtract.
I guess like so he's using S to count how many like valid prefixes of a set list like have been seen so far.
So
like
that's I guess that's what okay, but the prefix, does it the prefix end at 2 or the prefix end without the 2? So
yeah, so like so S would be like it either ends with a 1 or a 2. It's counting those chains. And so like if you see a 1, then that like creates a new chain. And if you see a 2, then like you can take each chain and either keep it as it is or also add a 2. So they multiply by 2. And
yeah,
then you add the 3, then then you have to get rid of all the chains that end with 1. But that's exactly just how many 1s it has seen before.
Yeah.
Yeah, I believe I can believe it, even if it look a little bit suspicious, because for me, I think of in terms of ending at 1, ending at 2, I will use 2 separate things to keep track and then just do. But I can believe this will turns out to be equivalent, but it just looks a little bit suspicious.
My code was just like pretty simple. Was it G? Yeah. So I just if whenever you had the new digit was 1, then you just add 1. If it's 2, then you multiply by 2, and then if it's 3, then you just have this. I don't know. It makes more sense to me because like it's just like pure combinatorics basically. The way I thought about it, but Riley's explanation makes more sense in like a sort of like constructive sort of way.
Actually, I think I have like a maybe an interesting way to think about it, like that can be more general than this problem.
Go ahead.
Okay, I think I'll share. Okay, you can see. Whoops.
Yeah.
So something you can notice is that a valid set list is actually like a regular expression that looks like this, right? Like a valid set list looks like this.
Yeah.
If you're familiar with regular expressions. So you can write a DFA like this. So in general, if you want to count the number of substrings that match your regular expression, you can do like a DP where you maintain 4 states. Like let's say you count S0, S1, S2, S3. So then if you see a 1, then you should increase S1 by S0. If you see a 2, you should increase S2 by S1 plus S2. If you see a 3, you should increase S3 by S2. So it's kind of overkill for this problem, I think. But in general, if you see like that what they're describing is a regular expression, then you can do like a DP like this.
Yeah, so that's this is what I had in mind. So I didn't code it as Harry to code it, but this is what I had. This couple variable maintaining this update this way. Yeah.
So an example of something this can handle more generally would be like you have some pattern string and you want to know how many ways it can be, how many ways it appears as a subsequence in a given text.
Yeah, but yeah, I guess I should say what I had in mind is not the regular expression, just thinking about this construction, and then it's the same update, but without thinking in terms of the finite state automata. So I guess when this thing gets really complicated, then having this finite state automata in mind will make it easier to think.
Yeah, so it's pretty overkill, or but it's like it's about like the most general way you could like think about something like this, and it can be good to know, I guess.
So yeah, and then actually I want to say just one thing about problem M actually. So it's actually the piano theorem is actually real. It actually existed. So I don't know, Riley, did you encounter that in any of your math course? So this is kind of I guess around the term from beginning of 20th century, where mathematicians try to put all mathematics on supposedly really rigorous foundation. So they get rid of everything, just start from 0 and then success of 0, and then define everything using this. So this is something actually existed. It's not just made up for the problem.
Yes. Yeah. I don't think I've seen it in a class, but yeah, I'm familiar with piano arithmetic to like to actually define integers.
Yeah, using this.
What's more common is to see like how rationals are defined from integers and how reals are defined from rationals. But yeah, it's fun. Should I discuss the geometry?
So sure, yeah. So I assume conceptually they are not the
B is pretty simple conceptually. E is not.
Okay,
I think.
let's do B.
Both kind of hard to implement.
Yeah.
So for B, you're given some polygon, say it's like this. Then you want to say put a camera inside the polygon so that it can see the entire area. So like an edge of the polygon would block its vision, like you can think like it's a wall in a museum or something. So you want to know, like consider the region of points where you can put a camera where it would see everything. And you want to know what's the area of that region. And yeah, that's the problem. So you can kind of see visually, like, what does this region look like in the picture? You can kind of see that like this line extends and creates a border for this blue region. You can kind of see that, you can see a similar thing with the other edges. So that kind of gives a hint to what the solution is. But yeah, so we have a polygon, and each edge, the area, so the edges are given in clockwise order. So that means if this edge is pointed this way, that means it has to be on the right of this line. Because if it was over here, it would have to like be out. If it was here and it was looking at this edge, it would have to be outside of the polygon, like before it sees it. So that means it would have to intersect an edge. So basically for each edge of the polygon, it creates a line and an area that it has, like of which side of the line it has to be on. So essentially the problem is like we're given a bunch of half planes and we have to find the area of their intersection. And so it's easy to see why, like, if something can see all the polygon, it must be in this region, but it's also true that if anything's in this region, then it can see all the edges. The reason is, like, say it was in the, say this point is in the region, then it has some edge, then it has some line to the edge. But if you suppose that it couldn't see it, like it would have to be entirely blocked. So this is inside the polygon and this is inside the polygon. But then it would have to like cross this again in order for it to enter the polygon again. But we already told that it would have to be on this side of like these edges. So it's necessary and sufficient. So we just want to find the area of this intersection given a bunch of lines. Oops. And the way you can do this is, so first there's vertical lines. We can treat that as a special case. So like, let's say that there's some lines where it should be on the right of these and it should be on the left of these. We can maintain like, the intersection of these intervals. So we know that it must be like, the x coordinate must be within some range L to R. So we can treat vertical lines like that. Then we can separate the lines by if they should be above lines or below. Like let's say that the point has to be above all of these lines. Then what we should, yeah. I guess I drew a kind of boring example. Okay, it should be above all of these lines. So it should be like on here or above. And this is sometimes known as like convex hull trick. So what this can do is, given a set of lines, you can compute like you can compute the boundary of like the region above all of the lines in log n. It should be in, it's also in like KCTL library. They call it like line container. You can check that out. So yeah, essentially, we can use our library to compute like this boundary. And we do the same thing with the lower lines. So like we have some regions like this. And we want to compute the area enclosed by them. And then what we can do is like, we can sort of sweep this area. So an interesting point would be like where you move from one line to another, and also when two lines intersect. So then as you like sweep this area, you can like consider each trapezoid separately, and you consider like if it's over here, then it has to be above this and below this, but that's impossible, so you don't add anything. And over here, it has to be below this line and above this line, so it's consistent. So you add like the area of this trapezoid to your answer. I guess I should say also like the vertical line come in. So like an interesting point would also be where you have the left vertical line and the right vertical line if they exist. But yeah, you can add the areas of these trapezoids and then you have the answer.
Okay. So basically, the line, each of the half space is either tilted upward or downward, or the defined by this vertical line.
Mm-hmm. So yeah, the general problem is like half plane intersection.
Yeah.
So that's how you solve B. I can move on to E.
Mm-hmm.
There's actually many steps to it. So let's see. So the problem's like this, where there's points in 2D space that they call components, and some of the components are leaking and you don't know which ones. But each component did a test, and you know the results of, well, not all of them. Some of the components did a test, and you know the results of the tests. So a test will be positive if at least one component in this triangle is leaking, and it will be negative if nothing in like the triangle it can see is leaking. So basically the input is, you know, the coordinates of all the points and then the results of the tests, or a dash if it didn't do a test.
So how is the region defined from the point? It's
the way they describe it is that if you move 1 unit up, then the triangle expands by 1 unit.
okay. So it's
so you could think like from
what
a point,
angle is it?
From a point, like it would be this vector 1, 2, and it would be this vector minus 1, 2. So anything that's like to the right of this vector and to the left of the other vector.
So that's like 90 degree. That 90-degree angle.
No, it's not 90 degrees.
You go up by 1. You go right to 1. Go left by 1.
It says like if you go up by 1,
Mm-hmm.
then this length is 1.
Oh, okay. That
So that
total
means,
length is 1. I see.
So that actually means the amount.
I see.
So that means like this length.
That is half. Yeah. 1 half. Okay.
So I just scaled by 2. So okay, so a point can see everything in like that triangle, or I guess cone, however you call it. But yeah, okay, so the actual problem is, given the results of the tests and where all the components are, you want to know the minimum number of components that could be leaking to be consistent with the test results. Also, you should output impossible if they contradict each other. So for example, if we see a negative test here and we see a positive test here, then the negative test, it can see everything that the positive test can, so it's actually a contradiction. So like if there's a leaking component here, the negative test should have spotted it as well. So the first thing I do is actually like to address the most annoying part of the problem, which is like there's this random 2 angles that they chose. And what we can actually do is say for a point XY, we would prefer it if we could say like it can see in orthogonal directions, like it can see to the right and up. So we can actually transform the coordinates like this. So like we'll transform it to a new point where it stores how far it is in the directions orthogonal to 1 and sorry, it was -1, 2 and 1, 2. So orthogonal to these would mean like 2, 1 and 2, -1. So you would transform the points like 2x plus y by doing dot product and 2x minus y. So I transform all of the points like this. So now I can think about what direction a point can see in terms of it can see to the right and it can see up. Like I just do a linear transformation on everything. Is this part clear?
So this is it's like a rotation plus a little bit like angle scaling, or what's into?
Like it's a linear transformation on.
I know. I'm just saying but this angle, whatever it is, become right angle in your after transformation, right? The viewable area.
Yeah.
Okay.
So instead of like this awkward triangle, it's actually
this. So
C is right and up.
So the transformation, it had both the rotation effect and also some kind of stretching, so that angle.
Yeah.
Yeah. Okay. So the transformation can achieve that.
And the reason that looking to the right and up is more useful to think about is because doing something like sorting by X or Y, makes sense. Okay, so let's think about the problem. So let's say the easier part is how do we check if it's impossible? So it's impossible if there's an N that can see a P. So what we can do is sort the points like by X and then by Y. And then scan them in that order. Every time we see an N, we'll keep track of what's the minimum Y coordinate of an N that we saw. And then if we see a P, we compare it with that Y coordinate that we're storing. So then if it's above, that means it's a contradiction, like it's impossible. And if it's below, that means it's okay so far. So basically, we can tell for every point if there's an N that can see it. And if an N can see it, that means it cannot be leaking. So that means it's also useful information for a dash. Like if you have a dash that an N can see, we shouldn't consider it as leaking. But if there's a dash that an N cannot see, that means it could be leaking or not. And we can like choose that. So also move on to saying, let's say that there's a P that can see another P. So whatever we choose as leaking, if it's consistent with this P, then it's also consistent with this P. So we should only consider, we should consider what we need in order to make like P's that cannot see other P's consistent. And then once we have those, we can be sure that we handled everything. So doing a similar thing, we can tell for every P whether another P can see it. So let's say we maintain the coordinates of all of these like interesting points. So as X increases, then Y decreases. So we can't have something like this because this sees this. Okay, is this clear so far?
Yeah. So then is it just counting the number of these points, or there's still more steps?
It's not that simple because there could be like a dash up here.
Oh, I see.
If we make this leaking, then it would handle all of these.
Oh, I see, I see, I see.
So actually I was stuck in like this part for a long time thinking about what we can do. I was thinking about like greedy things like if we're sorting in order and there's a dash, then we should make it leaking. If let's say if it takes out 2 or more points. But actually greedy is not the right way to think about this. So consider some like dash that's out here. Again, we're only considering the dashes that cannot be seen by an n. So each dash will cover anything left and down from it. So this dash will cover like these 3 points. This dash will cover all. We can, so you can see that because of like the structure of these points that like they're always like x is increasing, y is decreasing. A dash will actually cover some interval of points in like the sort of x order. It's like if I number these points like 1, 2, 3, 4, 5. So like a dash will cover 1 and 2. Something covers like all of them. Something covers 3, 4, 5. So actually, we've reduced it to like a non-geometric problem. So we have like we have n points, and we have some intervals, and we want to know what's the smallest number of intervals to cover all the points. Also, I can say like because we can make each p leaking, we can have like intervals of length 1 on top of everything as well. So I've reduced it to this problem where we just have a bunch of intervals and we want to know what's the smallest number of intervals to cover everything.
It's dp?
Yes. So you can do this problem with dp by saying, like for each point, it'll be covered by some interval. We might as well make it the longest interval that ends with it. Right? And then to cover everything else, we will do the smallest dp in this range. So the way I did it was like a range minimum query. So like we take the minimum dp of this range and then use that to compute the next dp state. There might be a way without using a range minimum query, but I didn't have a lot of time.
Oh. Complicated problem.
It was pretty complicated with many steps.
I think this year the 3 keyboard kind of really changed the situation because this kind of thing is really difficult to get with 1 keyboard.
Mm-hmm. So should we talk about F and H?
Yeah. So sure, yeah, F and H. Yeah.
Okay, Trung.
Okay. Okay. Can you still see this? Oops,
Yeah.
not my video. All right. F and H. Let's do F first. Okay. So you're given like M critics. So each critic will have like an original value, AI, which will fall between 0 and M, which M is given. So, excuse me. So the critics will work something like this. Let's see. So each critic will consider like the average score of the previous. Okay, so the critics come in row. They will see the movies like in order, in some order. So each critic, the first critic will always give the score of M, regardless of what his original value is. Um, for each next critics, he will consider the value. Oops, he will consider the value. Come on, the average value of like the score of the film up to until that moment, and let's say the average value is X. If this X is larger or equals to A, if this X is less than or equals to AI, then this critics will give like the score of M. Or else if it's less than AI, the critics will give a score of 0. So as a demonstration, let's do this test. There we go. Let's say that, so this is the original value of the critics. We can reorder these critics. So let's say we reorder these critics such that the first critic will have the score of, oh my God, here's getting laggy. The first critic will get a score of 3. The second will get a score of 3. Like the second critic's value is 3. The third critic's value is 5. The fourth one is 10. And the fifth one is 1. So let's consider this like the score for the film. Originally, the score is 0. The first critics will always give the score, here M equals to 10. So the first critic will always give the score of 10, no matter what his original value is. The second critic will look at this average score, and if it's larger than his value, then he will simply does not give any value, like does not give any score. So because the average score is 10, this person does not give any score to this film. So the average score dropped to 5. The next one, consider the average score, and the average score is larger or equals to his original value. So he will add 10 to like the original score. So the score is 10, average is 5. So now the score is 20, and average is 20 over 3. The next one will also add 10 to the score because this average is less than or equals to his value. So the score now is 30, average is 30 over 4, and the last one does not add any value. So it ends up the average being 30 over 5. So essentially you're given these critics and you want to order them such that at the end, the average score is exactly K over N, where K is given. So with this, so here we have K equals to 30. So with this order, we can achieve that average. So basically you print out the order of the critics, and if it's impossible, then you print out impossible. So the first thing we want to see, this is very trivial, that is that K must be divisible by M, because like each time a critic will either just give no score or give the score of M. So that means that this K must be divisible by M. And not only that, the value K divided by M will be the number of critics that give the score, not the non-zero score, or that give the M score. So I will define that P equals to K divided by M will be the number of critics that considers the film good. Good means that he will give a non-zero score. So let's sort the values of the critics. 1, 3, 3, 5, 10. Okay, so one observation you can make is that the highest the P critics with the highest value will be the good critics, will be the critics that will consider the film good, and the remaining will be the critics that will consider the film bad. We can prove this by exchange argument. Basically, if there is one critic from here that considers the game good, but one like the film good, and one critic from this range that considers the film bad, then we can swap them and we still have like the same number of good reviews, basically. So so this is the first observation. The second observation is that the critics, the order of the critics that consider the film goods will go in this order. So like the first critic that will appear is 3, the second that will appear is 5, and the next will be 10. And for the critics that will consider the film bad, they will go in this order. So that means that basically,
why that? Why
it's also the exchange argument.
Okay.
You can try to exchange them and see that it will still give the same reviews. So basically, you have like 2 arrays to merge such that, like with some janky condition, such that at the end, all of these elements will give like the good reviews, and all of these elements in order will give the bad reviews. So what I did was to basically, at each moment, I try to pick up either the first from here or the first from here, depending on which will, like, if the first from here, if we take it out and he will say good, then we take him out. If the first from here, if we take him out and he says bad, then we'll take him out. Basically, that's my solution. Yeah, so yeah, that's F.
Because the exchange argument is the key here.
Yeah. I wasn't able to prove the exchange argument during the contest, but I proved it nonetheless. Or actually, I see how all people prove it nonetheless. But yeah, I actually guessed the correct solution.
Okay, cool.
Cool. So that's F. The last problem is H. Cool. Okay. So for this problem, so each day at the company, there's a company and there are like n days. For each day, you know, like the number that will be hired. Here, the number of people that are hired on the first day is 3. And you also know the number that the people that are, hired, the people that are hired and the people that are fired. So the company will hire and fire employee with like with the last in first out policy. The last person to be hired will be the first person. The last person to be hired will be the first person to be fired. So so let's see. There are 3 people that are hired on these days. There are 1 person that is fired on the second day. That means that one of these people will be fired on the second day. And there will be 1 more people that join, then 1 more person that joins. For the third day, there are 2 people that will be fired. So that means that this first person will be fired, and then this person will be fired. And so on. You get the idea. So for each day, the company will have basically like an HR employee or manager or something that will supervise all of the firing and hiring. So each day there is only 1 person that basically manages all of these hire-fire thing. You want the minimum number of manager, and you assign the manager to each day, such that for every employee, the manager that will hire that employee will be different from the manager that will fire the employee. So as an example, for this first test, you would need at least 3 managers, HR managers, and you will assign them with these, like the first manager will take care of the first day, and so on. You see from this array. And this assignment will ensure that no person will have the same manager that will hire them and fire them. Okay. So let's first try to ignore this whole thing first and try to see that like for each employee, what is the date of his hiring and its firing. So for example, we have established that there's one employee that will be hired on the day 1 and be fired on the day 2. There is one employee that will be hired on day 2 and be fired on day 3. There's also one employee that will be hired on day 1 and fired on day 3, and so on. So it turns out that we can build these hiring firing pair using a stack, basically using the last in first out order. Basically you maintain for each element in the stack, you maintain like the group of employees that come from the same day and how many employees from that day that is still working. And then when it comes to hire, you basically try to pop out the back of the stack. Basically try to push out all of the employees that are hired to as close to the current day as possible. And yeah, and we can work all of these pairs out using stack in ON.
How many pairs?
There will be ON pairs. The reason for that is because like imagine how would I say this? So for a group of people, for each day, either a group of people is completely removed, like a group of people that are hired from the same day is completely removed, or they will be partially removed, like at the end here. We can notice that for each day, the number of groups that are partially removed is at most 1. So that sums out over like n days. The number of groups that are partially removed is ON. And also the number of groups that will be completely removed, that is also ON because there are n groups. So that means that the number of like events, the number of pairs is ON. Okay, cool. So we have all of these pairs. Cool. Now, what to do with the manager thing? It turns out it's actually pretty simple. Let's consider the graph that consists of these pairs that basically transform this problem into finding the smallest chromatic number, finding the smallest coloring of these edges, of these nodes, such that no edge connects the same color, basically. So one property we notice with these edges is that they are in the last in first out order. Basically for any 2 edges, either they intersect at one point, they are completely overlapping, or they are completely separate. Basically like their innards are either completely separate or completely overlapping. In a way, there's no this case. So Riley managed to prove that the chromatic number of this graph is at most 3. We'll get back to that later. So the solution is pretty obvious. Try to color 1 first. Coloring 1 is very obvious. You basically try to see if there's any edge in the graph, and then try to color with 2. Coloring with 2 is also easy. Basically try to see if this is a bipartite graph or not. Okay, so if we have tried 1 and 2 and none works, then let's construct like how to do with 3. So let's consider a range like this. We notice that, let's say that the first and the last are connected by an edge. We will notice that there is at most only one other node in between them that is connected to both of them. That is because if there are 2 nodes like that, then they will overlap. Like there will be edges that will overlap partially, which makes it not satisfy the condition of the statement. So what to do with these 3 nodes? Assign these 3 nodes with the 3 distinct numbers, 3 distinct colors, 1, 3, 2, and then solve recursively for this range and solve recursively for this range. Yeah, that is the solution. And if the first and the last are not connected by an edge, then just color one end arbitrarily and then just compress the range down by 1. Yeah, so that's the solution. Color by 1, if not, then color by 2, if not, then we use this construction to color by 3.
Okay, cool.
Okay, yeah, that's it.
So that's it. Okay.
Yeah.
Okay, great. Yeah, let me stop.